Okay, and welcome back to everybody, and welcome those new people as well who are signing on. I see people are signing on here. My name is Miles Budimir. I'm the motion control editor with Design World Magazine, and I want to welcome you to today's webinar, which is entitled "Specifying the Perfect Encoder: How to Avoid the Most Common Encoder Errors." So we will get started here today. I want to start off by saying that today's webinar, is sponsored by Encoder Products Company, as well as US Digital as well. I want to thank them for their sponsorship. And a few housekeeping points here prior to starting. Everyone should know that this webinar will be able to be accessed afterwards at designworldonline.com and also via email. So everybody who registered for this webinar will get a copy of the webinar. At the end of both presentations, we will have a Q&A session, and if you there's a section over here for questions. So at any time during the webinar, if you think of a question you'd like to ask one of our panelists here, certainly go ahead and write that question in there, and we will do our best to get to it at the end of the presentation. And finally, if you would like to tweet about this webinar in real time, we have a hashtag for that, which is hashtag DWWebinar over on Twitter as well. So as I've already mentioned, I am the moderator for today's webinar, Miles Budimir. And we have two presenters today. We have Jim Stevens from US Digital and Dan Craner from Encoder Products. So let me give you just a little bit about their backgrounds. Let me start off with Dan here. So Dan currently is the Americas Division Sales Manager for Encoder Products. And he has served as a Field Sales Engineer, Western Regional Field Sales, Business Development Group Manager for Automation Components, and Division Sales Manager at Encoder Products. And that's a little bit about Dan. Jim Stevens, our other presenter, has over 28 years of experience in the motion control industry, and he currently serves as the Vice President of Sales and Marketing at US Digital. And Jim's specialty is in position feedback devices, specifically rotary and linear encoders. So that's a little bit about our presenters, and with that, I will turn it over to Dan. I will turn it over to Dan Craner now. So Dan, it's all yours.
Hello, and thank you for joining us today. And just a short bio of Encoder Products Company is we are a global designer and manufacturer of incremental and absolute encoders, and established in 1969 with both global administrative headquarters and then America's production facilities here in the great state of Idaho. The challenge that we have today when it comes to specifying feedback devices is somewhat represented here by this slide. Is that here we depict three encoders that all look about the same from three of many manufacturers, three part numbering conventions, and the challenge that is presented is how does building a part number translate into the specification of the right device for the unique application parameters and at the right price that fits your budget. Also, some additional challenges is that we are in a highly fragmented industry and application. Encoders can be defined as everything from the one that's on your little desktop printer to devices that go on into outer space to do robotics on Mars and everything in between. For the purposes of this dialogue in our short time together, I'm going to focus on the general industrial automation applications, and the other presenter will be providing more specific information and guidance as it relates to small motor mounts. Another challenge, if you will, when it comes to encoders is 50-plus years, there have been no standards associations. There is no IEC, no NEMA, or anything like that. There are what we would call industry standards, but the point there being is that I think trust and trust and verify is probably good advice. In order to do so, here we're going to skim the surface on 4 general areas of critical considerations when specifying an encoder. Excuse me, I need to take a drink of water. Sorry about that. But in addition to these, there are also others such as agency approval, interconnect and cabling, and then also soft issues such as regional global support, budgetary, et cetera, that would need to be taken into consideration. Our hope here is in the next few minutes together is to give you at least a nugget or two to put in your pocket to apply as the next opportunity arises. Here's a glimpse and an overview of, coming here, the screen near you soon. There we go. Of just some of the package styles that could be encountered and considered. And they do vary, and again, as I mentioned before, since there's limited association standards, that, excuse me. There we go. Excuse me, I need to
Excuse just a minute there. Dan had to step away, and this is his colleague Steve at the Encoder Products Company, and we'll just we'll carry on until he's able to rejoin us here. Really, as Dan had mentioned, we've got a variety of package styles represented here, everything under the sun, as far as shape, sizes, dimension, but really they boil down to 2 basic types that we'll use as our guideposts throughout the rest of the presentation here, and that is basically a bore style and shaft style encoders. 2 categories in male shafted encoders you see on the right side, and the other one being the bore or hollow bore or through bore. And just defining those 2, we have the through bore, as the name applies, passes all the way through the encoder. The blind hollow bore has a cover on the back side of the encoder. So what we're going to look at is just what considerations need to be kept in mind, and what leads us to consider choosing one versus the other in the specification process. So there are benefits to the hollow bore design over the past few decades as this package has become more popular. There are reasons that make it a beneficial choice. One of those being, of course, less hardware and incurred cost to apply a shaft encoder via a coupler or sprocket or belt or pulley. The cost of ownership of those items for installation and the installation itself. Those are added costs that may be a factor in your decision-making process as to whether you want to use a shaft or a blind hollow encoder. The through bore and blind hollow bore styles, as mentioned earlier, have become very popular, but there are times where a shaft encoder is the preferred choice, and some of those applications we see represented here are mobile and outdoor equipment, severe operating conditions. That could be temperature, it could be moisture related, but also washdown applications as well. So there are certainly good reasons to select the shaft encoder versus the hollow bore or blind hollow or a through bore. One of those considerations is environmental sealing, and we look at the shaft seal. If you think about the task of if you were to pick up a ballpoint pen and ask how is it easier to seal the diameter of that pen versus something closer to a 50-cent piece, the answer is obvious. It's just easier for us to maintain a seal on this smaller diameter versus a larger through bore. So the area that needs to be sealed is much shorter, and over time, when contaminants are presented to that seal interface, it just becomes more difficult over the lifetime of that encoder to keep it sealed. Shaft sealing is certainly one reason to consider using a shaft encoder. Second, we'd also give consideration to what kind of load is going to be placed on the encoder, radial or axial load. Here we see an example of a hollow bore encoder that was installed in order to move the encoder away from a heat source on the other end of this shaft. And the encoder here, this blind hollow bore encoder, is actually carrying the load of the shaft. And so hollow bore encoders and through bore encoders in general are not designed to carry a load. They're instead designed to float freely on a flexible anti-rotation mount that you see here. So in this case, the encoder is carrying a load that it wasn't intended to, and that's over the long haul going to greatly have shorten the life and the operational accuracy of that encoder. When we have radial loads, or if we need to apply a measuring wheel, of course, a shaft encoder is designed exactly for that, and can more readily handle that. Another consideration: take note of the bearing. If you do select a shaft encoder, just take note of the bearings and the anticipated peak loads and shock that might be encountered in operational life. Less load is longer mechanical life. Also, maximum speed, duty cycle, temperatures impact longevity as well. Here are two shaft encoders with greatly different range of bearing load capabilities, and just take into account, make sure you're specifying the encoder with the proper capability for your application. And regardless of our best intents in designing and configuring encoders for their application, the end customer may figure out a way to use that encoder is not intended. In any case, the encoder is not a step. We've seen that take place in the marketplace, in the end user market. So, transitioning from mechanical considerations to electrical, and at least half of the inquiries we receive here from customers have to deal with questions such as you see represented here. We get suspicious when we hear things like the encoder was bad out of the box. We don't build them and ship them that way. They're all tested before they leave the door. Generally, when we encounter some of these types of issues that are spurious and intermittent signals, we start looking at electrical interconnects and those types of things, wiring, cabling. And one problem that's encountered quite regularly is signal noise, and this presents itself in sort of intermittent counts and signal disruptions. One recommendation we have to overcome that potential problem is whenever possible, we like to specify the differential line driver output. This provides capability for error checking due to the complementary signals on each of the channels, and the ability to drive voltage over long distances as well. So that would be our default recommendation. Of course, not always possible, but whenever possible, we would recommend that. In addition to specifying the encoder itself, also give attention to the cable and the interconnect. And we always recommend using a shielded cable with the line driver with the complementary outputs, twisted pair cable as well. And then, of course, good cable routing and connecting and termination practices also are part of the formula for success here. In addition to the electrical features, we also want to give some attention to environmental considerations and IP ratings. Here we see an example of an encoder that was subject to conditions that exceeded its environmental ratings. In this particular case, the liquid, the solvents, I think it was, worked its way down through the connector into the housing and had the impact that you see here. Quick word about IP ratings that you should be familiar with. The rating system standards, if you look at most of these here, even up to IP66, they do say limited ingress is permitted. And even with IP67, it's immersion for 30 minutes. These don't translate into allowing the maintenance worker to direct the 500 psi stream of water directly on the encoder for 20 minutes without any consequences. So just be sure that you're taking the full measure of the actual IP standard and how it's applied to the encoder, and again, in your application. And remember also there are 3 pathways of ingress into the encoder through the connector, the case and hub interface, and the shaft seal. And sometimes manufacturers do not always list or consider all 3 routes of ingress when they apply a rating standard to the encoder. So be sure all 3 routes are covered with the rating. So just in general terms, specifying an appropriate IP rating for all operating conditions, and this would include maintenance. How does the end customer intend to treat that encoder throughout the life of its installation. Consider all the ingress pathways, the housing connector, and understanding the standard. And more importantly as well, how does the manufacturer apply and implement those standards? More is not always better. When it comes to shaft seals, higher shaft seal rating, IP rating, will increase the breakaway torque and also can produce some heat over time, particularly at high speed. So the IP rating does have some potential unanticipated consequences. So more is not always better. Well, hopefully today we have supplied you with a couple of nuggets to apply both at the field use and in the specification process. And these are just a few things that we've encountered over the decades as a encoder manufacturer. Not totally comprehensive, of course, but Thank you for your time and attention, and Mr. Craner will be rejoining us for the Q&A session.
Okay, well, thank you, Steve, for ably filling in there for Dan. I hope everything's fine there. I hope it's just a business matter or something. And thank you again for your part of this presentation. So we will now turn it over to Jim Stevens from US Digital. So Jim, the floor is yours.
Okay, thank you very much. And thank you, Steve and Dan, for the great information on encoders. A lot of knowledge there, a lot of history, and actually a lot of common sense that was demonstrated in that previous presentation. So, welcome to the truth behind KIT encoder positional accuracy. So we're going to go a little bit different direction here in this discussion, but first, just to introduce myself once again, I'm Jim Stevens, VP of Sales and Marketing at US Digital. And US Digital is a US-based manufacturer of motion control products in Vancouver, Washington, for over 30 years. So Vancouver, Washington being Southwest Washington State, not Vancouver, BC. And today we'll talk about the positional accuracy of a KIT or modular style encoder. But first, before we progress here, we need to talk about what we mean by positional accuracy. Positional accuracy is the position of a shaft after it's been moved using encoder counts to rotate to like a particular location, like 180 degrees. You stop at 180 degrees using encoder counts, and you stop there with some kind of accuracy. It's 180 degrees plus or minus some tolerance. Okay, and also the KIT or modular style encoder, like Dan alluded to at the beginning of his presentation, is a different type of product than the bearing type encoders. The KIT or modular encoder arrives to a customer as essentially a bunch of parts. Okay, these parts are then assembled to an existing shaft and bearing assembly. That shaft and bearing assembly maintains the optics with respect to each other, and is really the controlling feature of the accuracy. And we'll dig into that here later on further slides. So, to start with, positional accuracy misconceptions. Okay, so accuracy is cumulative with every rotation of the shaft, encoder disk essentially. That's a common thing we run into here, is that people think that accuracy accumulates as you rotate the shaft. It gets worse to the point where the system is totally out of spec. Accuracy is a function of disk to sensor gap spacing, another misconception we run into quite often. And also, calculating encoder accuracy is nearly impossible. Nothing's impossible. We'll move forward here. So, positional accuracy. This is the formula used to calculate positional accuracy for a KIT encoder. Okay, this formula uses something called TIR, total indicated runout, and optical radius, and the arc length of that quotient, and 60 times that arc length gives an error in arc minutes. Okay, and just a refresher once again, one mechanical degree is equal to 60 arc minutes. So first in this formula, we'll talk about the optical radius. Okay, the optical radius represents the distance inside the encoder from the center of the optics to essentially the center of the reading track of the sensor of the encoder. Okay, and we'll do an illustration here to show what that really means in the next slides here. Okay, so we have an optical detector. We have a shaft, okay, which is the center of the optics in this case. We have a hub disk assembly and a set screw. Okay, a hub disk assembly consists of a disk pattern. Okay, this disk could be mylar, it could be glass, it could be metal, it could be multiple medias, many medias. Okay, the disk itself is attached to some kind of what we call a hub, which holds the disk in place to a mechanical system such as a shaft, and the hub is locked in place usually with a set screw on the shaft. keep the shaft and disc hub assembly rotating together. Okay, and in this case, you see the arrow here, the blue arrow. This is what is commonly called the optical radius of the encoder. Okay, and this piece of information, if you're doing this calculation yourself, it is available from the encoder manufacturer. They should be able to provide this information to you fairly easily. Okay, moving forward. Next component we'll talk about is TIR, total indicator runout. Okay, and really what this number is, what this number will be, is the amount at which the pattern moves relative to the encoder sensor in a radial form. Okay, it has nothing to do with the z-axis movement in terms of air gap between the sensor and the disc, but just primarily the run out of the pattern as it rotates relative to the sensor of the encoder. And in this case, TIR is composed of two main components. We're also assuming in this case that the shaft we're mounting to, like for example, a stepper motor tail shaft, is perfect. Okay, this motor tail shaft does not have any TIR. If that tail shaft did have TIR, there would be one more component added to this equation. It would be disc error, hub shaft differences, and the shaft TIR. But in this case, just for simplicity, we have a perfect shaft. Okay. So first thing we'll talk about is disc errors. TIR as it applies to disc errors. Okay. This is a typical optical system once again. This is a perfectly centered disc. As you can see, the disc is centered perfectly. There's the hole in the center of the disc and the hub are all perfectly centered. In this case, there's no TIR as you rotate the disc, and then it also results in zero positional error. But in reality, the goal of every encoder manufacturer is to get their disc perfectly centered, correct? But things can happen. The hole in the disc could not be perfectly in the center of the pattern. Okay, when the disc is installed on the hub assembly, the mechanical assembly that holds the disc, it could not be perfectly centered at that point. And as you can see in this picture, if you were to rotate this disc about that center axis, this thing will run in an elliptical orbit, and that will cause positional error in this system because the disc pattern's moving radially relative to the sensor, encoder sensor. Okay. The next component of the TIR calculation has to do with the hub inside diameter, okay, and the shaft outside diameter. Okay, and we'll move on to the next slide here. And we're back to our optical system. We have our read head once again. We have our disc mounted to a hub assembly. In this case, notice the set screw. It's not tightened in this case. And in order to assemble a hub disc assembly onto a shaft, the bore of the hub disc assembly has to be slightly larger than the diameter, outside diameter of the shaft. Okay. If they were the same size, it would be a press-on type situation. In this case, we have assemblies that go on very easily. So there's a clearance. So notice the set screw in this case, everything's centered. We'll step to the next slide here. We'll see what happens. So as we tighten the set screw, the difference between the hub inside diameter and the shaft outside diameter is pushed off to one side. And you can see this by this little blue arrow here. Once again, the disc is no longer centered in the system due to this error component. Okay. So back to our formula once again. We have some components here. And the way that error represents itself in an encoder due to TIR, to positional error, it'd be a cyclic error. Okay, so as you rotate your encoder shaft or your motor shaft, at which this device is connected, over one rotation, you'll see your error go from maximum to a minimum back to a starting point. It's non-cumulative. You'll see the full range of error over one rotation of the shaft. Okay, so in this situation, you can see that the gap between that the sensor and the disc is not represented in the equation in any place. So it's really not an error component. Of course, the gap between the sensor and disc have to be within the manufacturer's operating conditions to maintain a stable signal. If you get outside those conditions, all bets are off, of course. Okay. Now let's just do a simple calculation, a sample calculation. Suppose we have an optical radius of 0.433 inches. We have a disc error. The center of the hole in the disc is off by 1/1000th of an inch. Okay. And we have a hub that has a range of 0.2501 to 0.2506 for its bore tolerance. Okay. And the shaft we're attaching it to on the back of a stepper motor or brushless DC motor, whatever, has a diameter of 0.2498. Okay. So the first thing we have to do is we have to calculate our total possible total indicated runout. Okay, so once again, we take our disc error that we know is 0.001. Okay, then we take our maximum hub diameter, which in this case is 0.2506, and we take our shaft diameter, which is 0.2498. And this results in a total possible runout of 1.8 thousandths of an inch, 0.0018 inches. Okay, and the key here is that indeed you have to take the worst case situation where these tolerances add up. You know, many times these tolerances will subtract from each other and tend to zero out the errors. So the disc error will subtract from the hub disc or the hub diameter, shaft diameter error. Okay, but you really can't bank on that, right? At some point in time, these tolerances will add up, and you'll see the total maximum amount of runout. So you have to design to that condition. So crank the numbers through our equation. We end up of an error of 14.3 arc minutes. Okay, so that is the total possible error, positional error from this modular or kit style encoder. And this will be the number you'd have to design to in your mechanical system to ensure proper operation, regardless of conditions. So once again, looking at our curve, our waveform, we'll see that we have 14.3 arc minutes as a maximum error as you rotate through 360 degrees of the shaft. Okay, once again, it's a cyclic error. So you will see the entire error over one rotation of the shaft. Okay, and the error in this case, we show a nice sine wave. It could be quite a bit different than this, right? It could be jerky. It could be have discontinuities in the sine wave, and really this error is very repeatable. Okay, it's a repeatable feature opportunity, but as long as your mechanical system is stable, if your mechanical system is stable over rotation, the error component will always be the same. So this concludes our discussion about positional error as it applies to kit and modular encoders. I thank you for your time. Once again, I'll pass this back to you, Miles.
Okay, Jim. Thank you very much for your part of the presentation here today. And I think what we'll do now is open it up to some questions from the audience out there. So if you do have any questions, please feel free to type them in there on your screen, and we'll try to get to as many questions as we can here. So, and then also too on the screen that you're looking at here, you can see some of our contact info there. You see my contact info, but more importantly, you see Jim and Dan's contact info there too, because they're the guys that you probably want to talk to. So we do have a few questions here, so I'm going to go ahead and start. Let's see here. So we have, and hopefully these people are still on here, but we have a question from Adriana Otero, and it's kind of a two-part question. And I think this one, I think this question is aimed at you, Jim.
Okay.
And the question is, could you use this encoder to measure the position of a hydraulic motor that only does 24 turns to the right to open a choke? Kind of the first part, but also would it give you an output when the motor moves very slowly? I think it's kind of like a two-part question there.
Sure, sure. Yeah, indeed, an encoder. And in this case, the slides that we are showing here represents an incremental encoder. Okay, an incremental encoder essentially just puts out a series of square waves on a couple channels, right? And it's the responsibility of the controller to count these square waves to maintain position. So if you had a linear system that has some way to convert the linear motion into rotary signals, this type of encoder could be used on it for sure. You can maintain position over many turns as long as you maintain your count, your counting of the edges of the encoder signal, square waves coming out. If you happen to lose that count with an incremental encoder, you lose position, and you have to back up to a known location, essentially home the system, and restart your counting again. Okay. So to answer Adriana's question, yes, definitely this type of encoder could be applied to their system as long as they convert their rotary motion or their linear motion to rotary signals.
Okay. And I guess okay, so I've got one more follow-up from Adriana, and the question is, if we lost power, could we still retain the position that the motor is at? And I guess that would depend on what if it was an absolute encoder, right?
Yes,
is that correct?
That's correct. This is once again Jim from US Digital.
Yeah.
Yes, that's a true statement. Incremental encoders are relative. Once again, you have to count edges to maintain position. Absolute encoders give you true position regardless of if you lose power, turn and turn back on. They give you true position.
Right. Okay. Okay. Let's go to another question here. Here's a question from Seth Kaufman, and he wants to know what about the error due to the limits of the encoder resolution, something like half of the ENOB.
Okay, so I'm not quite sure what the question is, but this is a common subject: encoder resolution versus accuracy.
Right.
Okay. So, many times over the years we run into people saying, "Well, gee whiz, I want more accuracy, so I'm going to buy the highest resolution encoder I can purchase." Okay. So, let's say they go out and buy a 3600 CPR encoder. Okay. So they want to be able to take this encoder and break their circle, their rotary motion into 3600 pieces, and be able to position within that circle. Okay. But if you had a 3600 CPR encoder, and let's say you had a 360 CPR encoder, so you got an order of magnitude difference in resolution. Okay. So in your system, in your control system, suppose you want to try to position your system to 180 degrees, or 100 or 1800 CPR, or 180 CPR, depending on the resolution of the encoder. Okay. Your system stops. Okay, stops on the encoder edge, but when it stops, the accuracy is the same. If both encoders have the same accuracy specification, the accuracy remains the same. So you stop within plus or minus some accuracy tolerance, regardless of resolution. So that is a very common question. That is an extremely common question. Sometimes people spend a lot of money buying a very high resolution encoder when they really don't need that resolution, thinking that they're buying more accuracy.
Okay. All right. Okay. Here's a question for well, Dan or Steve. I'm not sure which one of you guys is there still, but are you guys there, or Steve?
Yeah, this is Steve. Dan wasn't able to rejoin us. He's been fighting a bug that got the best of him and made it unable to continue on here. So.
Oh, okay. Sorry to hear that.
We'll try to carry the ball in his absence.
Okay. Well, hope he's feeling better. Wanted to a question that kind of references back to something you guys said earlier, which was about the idea of more is not better when you were talking about I believe it was the shaft seals.
Mm-hmm.
When you said that shaft seals can impact the breakaway torque, how exactly so, or I guess why is that, or kind of how does that work? I guess that's the question there.
Yeah. Well, just the shaft seal. Let's say, for example, we have one shaft seal that's at an IP64 rating, and the same encoder could have an IP66 rating. The seal material is thicker. There's going to be a thicker lip contacting the shaft, and so, for example, on the IP64 shaft seal, you might have a breakaway of 1 ounce inch versus 3 ounce inches on the IP66 shaft seal. So it's going to take more force to instigate the rotation of that shaft because of the tighter seal,
Mm-hmm.
Greater sealing surface with the higher rated seal.
Okay, I got you. Okay. All right. Here's another question. Maybe sounds like this one might be for Jim. As kind of a clarification, Bob, let's see, what's his name? Bob Loy here has a question. He says he's kind of a newbie here, but I wanted to know what the difference is between modular and kit encoder, or is that the same thing, or is that too different?
Good question. Very good question.
Okay.
Really, they're basically the same thing. The terms are used interchangeably quite a bit. Kit encoders, modular encoders.
Mm-hmm.
Really, it boils down to that they require a user or a customer shaft to be attached, Mm-hmm. They're purchased. They come as essentially a bag of parts. Essentially, you have a disc assembly. You have some kind of a rehead assembly. You have a base plate and a cover, and they're assembled onto an existing system. So, really, in the industry, those terms are used interchangeably quite a bit.
Okay.
Versus the type you saw in the first presentation from Encoder products, those are more of they're bearing encoders you saw on there, hollow shaft or shafted styles,
mm-hmm.
which the encoders have their own set of bearings. They maintain their own optics integrity inside mechanically. Not rely upon an external shaft system to maintain their TIR essentially or accuracy.
Okay. All right. Let's go to another question here. This is from Jayender, and he has a question about. He says, does a high CPR encoder allow you to command a finer turn?
Okay. Yeah, that's a good point. So what high CPR buys you, okay, it breaks your circle into a finer resolution. So if you have a 360 CPR encoder, essentially not counting quadrature counting, but that's something else. We won't talk about that here. You can position to 1 degree. If you have a 3600 CPR encoder, you can position to 1/10 of a degree. Okay, so it breaks your circle into a smaller component.
Mm-hmm.
So it allows you to position, but once again, once you position to that point, you have a tolerance given a kit or a modular type encoder.
Mm-hmm.
So you have a tolerance. You're positioned to 1/10 of a degree plus or minus some tolerance.
Okay. All right. Let's go to some other questions here. So here's one came in from Michael Miller, and he's asking a question here. He says, when using an encoder as a master signal for a motion control system that is camming or gearing, do you have a recommendation for resolution of the master versus the slave? And I guess that could be for both of you guys too, I guess, right?
Interesting question. I don't have that's a lot more about the system.
Okay.
In order to provide a recommendation, there's a lot of variables in the mechanical system.
Mm-hmm.
There's a lot of variables in controllers, your servo loop gain, amplifier. There's a lot of variables. So really, I don't have from my perspective, a recommendation.
How about Steve? Anything you want to throw in there at all, or?
You know, I'd go along with Jim on this, and that there are so many variables in as far as what exactly we're hoping to accomplish, and all the components in between introduce their own factors. So without knowing more, I don't think give a meaningful answer.
Okay.
That's a tough one. Yeah.
Okay. Well, actually, Mike. Looks like there's a follow-up here from him, maybe kind of a bit of a clarification, but he says, I usually recommend that the counts per unit of the master to equivalent counts per unit of slave be matched. I don't know if that helps clarify anything. But yes or no? Or would it just be a matter of kind of knowing some more about
it's
some more
really
details
knowing
on the system, I guess.
Yeah, you really have to have some more details about the entire system.
Okay.
You could throw some numbers out, but without knowing the intimate details of the system, it's really hard to make a recommendation.
Okay. All right. Let's see what else here. Let's see. So here's another question here. In terms of, and this kind of goes to can go to both you guys here. But in terms of, let's say, what do you think is the number one question, the number one problem you get from customers or from people calling in terms of why their system doesn't work, let's say? I mean, you think is it a and I think actually, Steve, you might have referenced some of this earlier too. Where you mentioned some of those things that you often hear from people, like, well, we pulled it out of the box and it wasn't working, or et cetera, et cetera.
One of the I'd have to say certainly in the top three to answer that question, and I, if you spoke to different folks who had spent time in the customer service queue or applications engineering, or one of the questions that certainly arises with frequency, or issues, I should say, is a matter of the output type of the encoder does not match the input requirements of the receiving device. And sometimes this can be a function of someone's trying to do a field replacement, going from brand A to brand Z, and maybe we all use different manufacturers use different lingo to describe the same type of circuit, and so sometimes there's a little bit of misinterpretation of the terminology. Sometimes it's you may have the encoder and the specification process ends up at the very end, and somebody says, "Oh yeah, by the way, we need an encoder." And we may not have all the details on the receiving device, and so someone makes their best guess, and it was unfortunately incorrect. So our recommendation is always to have all the details, specifications of the receiving device as far as its input requirements clearly known before specifying the encoder. And that seems to be the best approach to take. So, but it is certainly something that crops up with frequency. I speak from my own experience answering the phones.
All right. Jim, anything?
Steve's absolutely correct. Steve's absolutely correct. He nailed that one on the head. The interface issue. The mechanics are pretty easy to figure out because they're very visible. Like Steve's mentioning there, you can throw a couple of encoders on a table. You can look at and say, yeah, this has the same shaft, has the same mounting, it has the same, physical constraints. That's usually pretty easy because, like I say, it's very visible. it's the interface, the electrical interface, the resolution. The things are not quite as tangible, right? That's usually the problems occur in applications, and it's usually a startup problem a lot of times with newer customers. Getting the first encoder, getting that product in there and operational to their expectation. Once the system's defined, it's easy, right? You just start shipping encoders that match the last one that worked, right?
Yeah.
But Steve's absolutely correct. The electrical interface a lot of times is really the hang up on the encoder application side.
Okay. All right, good. Looks like we got looks like there's another question here from Michael Miller, different question, and he's asking for any ideas for recommendations for mounting an encoder to a line to reduce vibration induced on the encoder by the main line shaft. So problems with vibration and noise, it looks like there. Any recommendations for mounting?
So I'll start. This is Jim again. More than likely, that would be a bearing type encoder on line. So I suspect you must be talking about like maybe a conveyor line or something like that. Steve, do you have any feel for that in terms of what you guys do?
Yeah, there's probably two ways to address that issue, and again, this is a situation where it really would prefer to see and have a few more details about exactly what what situation we're talking about, how much vibration, how do we quantify that? Because each encoder has a manufacturer will have its own shock and vibration limits specified, but a through-bore type encoder mounted directly to the shaft, the shock and vibration would be transmitted and carried by the flexible mount. So that may be an option that could could be satisfactory. Another possibility is to use a flexible coupling between a shaft encoder with a heavy bearing set and ample shock and vibration ratings, because the coupling device, flexible coupling, could mitigate some of that transmission of the vibration. But again, like a lot of some of these mechanical interface issues, it's knowing the full details help us provide a best possible answer. But that would be my two thoughts.
Right. Okay. Okay. Good. All right. Well, good then. So it looks like we're reaching the end here. It looks like we've gotten through pretty much all the questions here that we've been sent. So if we don't have any other questions, I guess we can go ahead and wrap it up. So I'd like to say thank you to everyone for coming and being with us here today for this webinar. And a couple of points here again, just before we say goodbye. The webinar will be at designworldonline.com, and also every person that registered will also get a copy of the webinar via email. The Twitter hashtag there as well, hashtag DWWebinar, if you wanted to make some more points about it. And also as well here for connecting with Design World and maybe keeping this conversation going as well. You have contact info for both Jim and Dan or Steve there, but also as well with Design World, our Twitter. You can follow us on Twitter there with the hashtag or at, I'm sorry, our handle on Twitter. At Design World, and our Facebook page as well. You can follow us on Facebook through the Engineering Exchange or our Design World LinkedIn group, and as well our YouTube channel as well. So there's many ways to connect and keep the conversation going, basically. So once again, I'd like to thank everyone for coming, joining us here, and obviously to Jim and Steve for stepping in for Dan there. You did an excellent job, I think. So thanks again to everyone, and have a good rest of the day. Thanks.
Thank you, Miles.
Thank you much, Miles.
Good.